And so our next speaker is Leibfried from the National Institute for Standards and Technology. And he will tell us some really interesting results, I'm sure.
Okay, now put this anywhere in your phone.
Can you hear me? Okay, great.
Okay, go ahead and share screen. All right. And with that, you should be good.
One more thing. I think just a little easier to see. Huh? Okay, great. All right. So first of all, thanks to the organizers for inviting me to give this talk here, and thanks to everyone who showed up on the last day. I hope I can find a place that's not too bad for the sound. Okay. So basically what I would like to tell you is how we think we can address the challenges in scaling up of trapped ion quantum information processors. And I hope most of you have been in Jungsang Kim's talk yesterday, because you can think of this talk as something of a continuation of that. Jungsang showed you, based on IonQ, what the state of the art in the industry is, or at least one of the companies. I'll talk a little bit about Quantinuum. Apparently it's not so well known, so maybe that gives you something new. But mostly I want to talk about things that are beyond what is done in industry right now. You may wonder why you want to do this, and I found the perfect motivation running yesterday on the campus of the University of Toronto. Basically, the impossible is a challenge, so we should take that challenge. And then University of Toronto students are actually asked to do something even harder. They should defy gravity. I think our task is a little easier. And then there was also this sign here that said there's a maximum speed that we can go at. So it will probably take a while before we get there. All right. With that said, I want to start a little and give you a little idea about how ion traps work, because we should be sharing our information so people can catch up. Basically, the idea with the radio frequency ion trap is that you can have a quadrupolar field. This is actually from Wolfgang Paul's Nobel Prize lecture. You can see there's a quadrupole potential here. And the decisive piece of that is that in some place in the middle of the quadrupole, the electric field vanishes. And it does not vanish all around it. And that creates something we call a pseudopotential. And all you need to know about the pseudopotential is that it's proportional to the electric field squared. So if you square that quadrupole, you get harmonic confinement in this pseudopotential. And the typical numbers for what we use here is the drive frequencies are 10 to 200 megahertz. And then depending on where you're driving and how hard you drive, you can get frequencies with which the ions move on the order of 1 to maybe 40 megahertz or so. Now, this trap is very well confined. It would be hard to interact with the ions or image them. But it turns out that you can unfold this geometry and make it a surface trap. So now the electrodes are in a plane. You still have a zero, and that's all you need. The ions want to go where the zero is. And then with laser cooling, you can make sure that their energy is minimized and they hang around in what's basically a one-dimensional channel that goes into the slide. Here's an example. This was the first surface electrode trap that trapped atomic ions, magnesium ions to be precise. And here you can see a few images with basically a microscope and a CCD. You can show these ions, and the distance between the ion and the surface here was in this experiment, oh wow, 40 microns, not 40 millimeters. So it's a very small distance, and that will become important later on. All right. So yeah, finally, we also want to make sure the ions don't go out through the ends of the trap, and we can put positive potentials here and here, and that will confine the ions also harmonically in the third dimension. So that's the basic idea how you can trap ions. Here I can just build on Zhangzhang's talk. What we want to use for our qubits are hyperfine ground states, and that's a very good memory. So actually our qubits probably won't need a lot of error correction as long as you don't compute on them. Why am I saying that? Basically, the T1 is something like 10,000s of years, and the T2 can even experimentally, so this is not a theoretical number, this is something that has been shown in an experiment in China. It can be larger than 1 hour. And then finally, you may worry that the qubits disappear, all of the qubits just disappear because, for example, they could collide with background gas in our experiments. They're just hanging all over the surface. But if we go to low temperature, we can have very good vacuum. And we have one ion trap where we keep a few ions for on the order of months, and typically we lose them because there's a user error. So they can have very long lifetime. We can also use so-called magnetic field first order insensitive transition. Basically, if you plot the magnetic field here in this direction, and then the shift of the qubit, it goes through a minimum, and in this minimum, it's first order insensitive to changes in the magnetic field. And for example, for magnesium 25, this is at 21.28 millitesla, and at that point, your qubit frequency is 1.6, well, 1.7 gigahertz roughly. So that's the kind of qubit frequency that I'm talking about. The operations on trapped ions, you can do single qubit rotations. So these can be fairly arbitrary. So you can also do non-Clifford gates if you wish, but of course you can do Clifford gates. And then the universal 2-qubit gates, you can use the Murmer-Sørensen gates that Zhangzhang introduced yesterday a little more. I'll just have you believe that because time's short. And there are other types of gates as well. The basic idea is almost always that you induce a phase shift on certain combinations of states and others stay the same. And all of these together then give you a universal gate set. So how well can we do this? We've just done a single qubit gate benchmarking on our magnesium qubits in a few weeks ago. And as I already said, the qubit frequency is at 1.68 gigahertz, so we can do this with microwaves. The basic idea of randomized benchmarking is that you take a random sequence of Clifford gates and you take another random sequence of Clifford gates and so on and so on. And you just run this on your qubit. Yeah, an algorithm could very well look like random gates if you don't know what it's doing. So this is a nice way to characterize your qubits. The one twist we did in this experiment is, since they're random, you don't necessarily need to put them all into a memory. That can be very expensive if you have to run long sequences. And in our case, we ran up to 100,000 gates. We rather produced the gates on the fly. So the FPGA decided on what the next gate will be while a gate was executed. And this can be done in such a way that if you have a pseudo-random number generator and you know the seed, you can actually reconstruct all of these gates, even if they're decided on the fly, because it's still a deterministic sequence, but it's pseudo-random. And then we can also compute the final stabilizer that returns to the measurement basis, and we update that. And then we just run this for L gates, and we do this for sequences that are hopefully unique if the pseudo-random generator is good. And so basically the way this looks is that we make our track while we are running. So anyways, how well does it work? Basically, in this way, we did over 1 billion fully random gate operations. And these are the blue dots are the observed success probabilities. You can fit this with different models. And basically, this is the take home. We can do the single qubit Clifford gates with error per Clifford of about 1.6 times 10 to the minus 6. And the gate duration for such a Clifford is 16 microseconds in our system. 2 qubit gates, it's a little more tricky. It takes more time. The nice thing about the surface electrode traps is that you can get very close to these surfaces, and that allows us to run magnetic currents here and have gradients of these currents that are non-zero. They can be fairly large, in fact. Why is that important? Essentially, ion traps use motion, as Changsang also explained yesterday, to couple the ions and the Coulomb interaction. So you have to have a way to get the motion excited. And one way you can do that is with gradients. Of course, this excitation has to be state dependent. And so in our case, we use the gradients of magnetic fields. If you just think about BOs of R, that's good enough to get a first order estimate. You know that the gradient, or maybe, well, the gradient does drop as 1 over the distance squared. And so if you're close enough, you can still get a gradient that's fairly sizable, even if the running wave, the free field K vector of such a 1.6 gigahertz field would be centimeters long, but the near field allows you to get a gradient. And so in this way, we can do gates with radio frequency and microwaves. In our demonstration, which is a while ago now, it was 2021 when it was published, we were able to do a gate error of about 10 to the minus 3, and the duration was 700 microseconds. But the good news is that this has been vastly outperformed by a recent experiment in Oxford, where they did a very similar gate, and their Bell state fidelity, they haven't yet run a randomized benchmarking on it, but I think they will do that soon. But in any case, the Bell state, which can stand in for gate fidelity, hopefully, was 3 times 10 to the minus 4 error. So we're getting closer to 10 to the minus 4, which for some people is a magic boundary where maybe you can do fault tolerance. And the gate time is still somewhat long, 120 microseconds, but you know, it has dropped quite a bit from the 2 years earlier demonstration. So there's some hope that we can make this even better. All right. So another thing, and since you stayed for the last day, I can tell you a few dirty secrets of the business of atoms. The qubit readout is typically done by fluorescence. So what I mean by that, we have our 2 qubit states down here. They're in the hyperfine ground states in the example I showed you. And now we need to read out. So typically what is done is you have a cycling transition, a very fast dipole transition where you can scatter thousands of photons in a few microseconds. The trouble is that when you scatter them, they go pretty much in random directions. And so you have no control where they go. And then you can think about what could that do to the rest of my qubits. If these qubits are the same qubits or in the same states as these two, then there is a pretty hard law what the scattering cross-section will be. It's basically non-negotiable. It just goes as the wavelength of the scattered light. And then the question is, how far away are you? Because basically what you have to compare is, you have this solid angle, say, for your detector, and then you have another solid angle to your bystander. And what's the ratio of these two angles? That decides how many of the photons will hit the bystander for a certain number of photons that go into the detector. So for 300 nanometers wavelength, the best case scenario, you don't have any stray light, your optics is perfect, but your atoms scatter when you do a mid-circuit readout or something like that. In that case, you can see that you have to keep the atoms or ions fairly distant, because at 10 microns distance, for example, you get a scattering probability that's already sizable and over 10 to the minus 4. So for mid-circuit readout, that would be a problem. There's a solution. What you can do is you can do an indirect readout. So you can have a helper ion. The helper is of a different species. So that's shown by the color here. And if that helper ion scatters light, the qubit doesn't care because it's a different wavelength and these scattering resonances are fairly narrow. So what you do is you basically use a 2-qubit gate that allows you to entangle the helper, which is in a known state to begin with the qubit. And then you have a state of this sort, and that would be an entangled state. But the moment you read out the helper, you collapse to have the same readout in the data and the helper. So it indirectly, you have found out what the data qubit is, and either the helper was already an ancilla, so this could have been a syndrome measurement, a very simple one, or you just now know that the qubit has the same state as the helper in this example. So in this way, you can find out without destroying the quantum information in the bystanders, and also by just projecting the helper, the qubit, you can find out which state you're in almost non-destructively. And yeah, I already said that the qubits are oblivious to the helper fluorescence. So the pros of this is that you can have a higher readout fidelity because this can even be repeated. Since the data qubit was projected, you can repeat this. And so you can avoid, but you can have higher readout fidelity at the price of a longer duration of this readout, of course. And you avoid the decoherence, and you can also make that helper syndrome or flag qubit, as I mentioned. So it's not necessarily one-to-one. You can also read a full stabilizer, let's say, into the helper and then read out the helper. So this could be fairly useful. We did a demonstration experiment. This was done with lasers. So there was actually spontaneous emission. And the spontaneous emission is a problem when you work with lasers. But what we could do, just to demonstrate how this would scale, is we could change the detuning of the Raman laser here. The farther the detuning, the fewer spontaneous emission events, but you need more laser power to do your experiment then. So there's a price for this. In any case, what we saw is that our readout fidelity pretty much scaled with the amount of decoherence from spontaneous emission. And we were able to show that we can read out the spin up state with about 10⁻⁴ error and the spin down state with about, well, in fact, we did 10⁵ experiments and we never saw it fail. So anyway, it's a very small error. So this is a nice way to do indirect readout, hopefully. We need to read out the helper, and this is typically done, for example, in the IonQ and also in the continuum systems with a big lens. So you basically take an image of your ion and you know where the ion is, and in this way you can find out which state it is in. That is not really scalable because the field of view of these objectives is only on the order of 100 microns by 100 microns or so. Maybe you can build a crazy system that's larger, but not easy. Instead, what we demonstrated is that you can put the detector directly into the trap, and that makes it scalable. You can see this trap over here. Here are the RF electrodes, and then the ions, we can load them over here, and then we can transport them over a detector. This is a superconducting nanowire detector here. So you have to run it at low temperature. In our case, we ran it at 3.5 Kelvin. And by using this detector, we were able to see that we can have fairly nice discrimination between bright and dark states. Notice that this is a logarithmic scale, so this overlap may seem a little crazy, but it's not so bad actually. Said in other ways, we can also use FPGAs again that can do things very fast, and we can do a Bayesian update. And this is shown here in the green curve, where basically the mean readout error is shown versus readout duration. And there's a minimum for the Bayesian updating. And of course, this is an average. So because it's Bayesian, it's not always the same duration. But in any case, for about 46 microseconds, you reach this. In 46 microseconds, you reach this minimum. And it's about 9 × 10⁻⁴. And as I said, if this is a helper readout, you can repeat this. So you can make it even better by reading out several times. So all of these things are not too bad, I think. Yeah, I already said we don't require imaging optics. Basically, there's nothing between the ion and the detector. And you can scale this with the trap. If your trap gets larger, you have more of these devices. And then you can have the parallel readout. You may wonder about the crosstalk, but it turns out that it's fairly minimal. So if an ion's over there, it's effectively isolated from scattering into the detector, and also the laser beam wouldn't hit it there. Anyways, so another dirty secret. Everyone likes to show their nice traps, and you may wonder, why does it look like a bow tie? The answer is the beams, the laser beams used in these devices are free space, and you can only focus a laser beam to a small spot over a fairly short distance. And basically the width of this bow tie is chosen such that you can focus your laser beam tight enough so you can work in this work zone here. So that's not scalable either. If you want to double or quadruple the size of the trap, either you build a very, very long trap that has this bow tie feature, or you are running out of room for your beam to be able to spread and not hit the trap. So what else can we do? This is not our work. This is work from ETH and Lincoln Labs. But in any case, I can leverage it here as an argument of how you could scale up. What you can see here is an example from ETH, where they integrated waveguides into the trap chip itself. Here you can see such a chip. And these things here are beamforming couplers. They're essentially gratings, curved gratings, like the one you can see here, that can make very nice Gaussian beams. This is a picture of the elliptical Gaussian beam that they formed in this way. You can see the cross sections here, and these two should depict the two ions. And using such a device, they were able to do entanglement of 240 calcium ions with a Bell state fidelity of 0.993. So that's not a world record, but this is with integrated optics. And of course, in the scenario I explained to you, we would use microwaves and RF for the entangling gates. We would just use this kind of thing for laser cooling of the ions and for readout and state preparation. The losses are not negligible in such waveguides, so it's 2 dB per centimeter. But if you only use it for readout light, you don't need a lot of power. For a readout beam, you need something on the order of microwatts, especially if you can focus as nicely as in these devices. And so naively, even if you had 1 million qubits, you would need something like a watt. And even if all of that is dumped into the chip, you would need a watt for all of them, so about a microwatt per ion. And even if all that heat is dumped into the chip, you could possibly remove it, because we're not in dilution refrigerator land. We are at 4 to 10 kelvins or so. And so the heat load can be fairly sizable there. Okay. So what I told you so far is that we can do gates with low error, and that we can drive them with RF and microwave. We can use these helper qubits for indirect readout and state preparation. So we can also have very low state preparation error by the fact that when you can do readout, you're basically projecting your state. And if that projecting is non-destructive, you can have a good state preparation if the readout's good. We can have integrated detectors in the trap, and we can have optical waveguides. So what I want to address in the final few minutes is how can we extrapolate this to a useful machine? So what would it look like? And of course, there's a lot of speculation here, and I'll probably be wrong in a few years, but that's the nature of the business. The idea is that if we really want to build such a machine, a scaled machine, then even today we have to think about how that could look like and make it compatible what we try today. If we go into a blind alley, that's not going to help us. Anyway, so what I want to talk about is a fault-tolerant machine that has about 1 million logical qubits. And the errors on state preparation, operations, and measurement should be on the order of 10⁻⁴ or less. And my friends in the error correction business tell me that this could be done at this kind of error level with order 10 physical qubits per logical qubit. Let's not argue about whether it's 10 or 20, but something like that. Okay, so how would it look like? Essentially, one way we could think of it is a big honeycomb lattice, basically, of ion traps. So these are not the atoms, these are the traps. And if you zoom in to one of these elements here, it could look like this. So this would be a junction, for example. The red electrodes are the RF electrodes, and the green electrodes are the DC electrodes. If we take a cut through here and look from the side, the ions would again hover a few 10 microns above the surface, and you've seen this picture already. There's a 0 of the electric field, and that's where they want to go. And that basically creates confining tubes along here and along here. Now, when we come to a junction, we also want to make sure that the ions go in a certain direction. So what we propose to do here, and this is not technology that works already, but potentially it could, we would basically want little switches here. So if we have that, we could, for example, switch this electrode to be on RF high. And now if you look at this again, it's basically your tunnel has a kink here, but essentially it's still a tunnel. The ion doesn't have to decide whether it wants to go here or here, it should only go here. So if I transport an ion, it should go this way. So just to explain what the colors here mean, the helper ions, those are the ones in blue, and the data ions are the ones in dark yellow or orange. And the data ions are supposed to travel, while the helper ions can actually stay stationary. They just hang around and wait for the data ions to come by. And so, for example, if I want to do a 2-qubit gate, I could bring in the qubit ions that I want to connect here. So by doing this transport, I can make sure that there's arbitrary connectivity in some limits. As the previous speaker pointed out, this takes time, and I'll address this in a moment. But in any case, I could possibly bring those two ions here together. And in this type of machine, you would never have long strings. You would only have relatively small strings of, say, 3 qubits. If you want to do a 2-qubit gate, you have your helper here. If there's any heating from the transport, then the helper ion can help you cool these two ions sympathetically without destroying their quantum information. And then you can do an entangling gate between these two, or you can also do an entangling gate between all 3 of them. If you want to do a syndrome readout, for example, you ask the questions, are these two in the same state or in a different state? That would be a stabilizer, a CZ. Or if you just want to do a readout of one of your ancillas in mid-circuit, let's say, you could have this confirmation here. So you just entangle the two, the helper and the qubit, and then you read out the helper. So that's the basic building blocks, how you would do quantum logic in arbitrary connectivity. So what's the commercial state of the art? This is pretty much the recipe that Quantinuum follows. Modulo, they don't have junctions yet. They actually have those in their research, but not something they've even published a few things about junctions. In any case, this is what the Quantinuum machine looks like. It's basically a racetrack. And in this very nice paper, they showed operation with 32 data and 32 helpers. This cartoon only shows the data ions, but basically there's one helper for each data, and if they do a gate, it actually looks like that. It's a 4-ion, very small crystal. And so they never have a lot of ions together. And the question that John Preskill asked yesterday, how can you keep track of all these modes? The answer in this case is we are stupid, we do it simple. We just have the modes from 4 ions rather than, say, 50. How well does it work? This is laser driven, not microwave driven. Their single qubit fidelity is already pretty good, 2.5 times 10 to the minus 5. The 2-qubit fidelity is about 2 times 10 to the minus 3. And they've done a lot of different algorithms, all quite successfully. There's one thing And again, another dirty secret. If you look at the budget of these circuits, there's something that's a bit alarming. The quantum operations are this first number here. And in percent, it's just 1 or 2%. So basically, the transport and the cooling takes 98 to 99% in these maybe representative algorithms. So we clearly have to have our work cut out to do here to do better with the transport and so on. And there are some ideas how that can be done. But let's assume we can overcome this. Oh yeah, and I should say this machine is now running with 56 qubits, and that's basically capacity. So you can't do much more in this system, but it's a very nice system, in my opinion. Anyway, so how could you then really scale this up, assuming that you can fix the problem with the transport and make it much faster? And by the way, the same problem is also present in Rydberg atoms. They have very fast gates, but then transporting the atoms around takes quite a while. So you can think about the geometry. How do you do this? The first idea, of course, is we just make it linear 1D. If you think about 10 to the 7 qubits, the minimal length, again, let's not argue about factors of 2, it's about 20 meters. And so if you have that qubit distance, even at a fairly large speed, 100 meters per second is not bad for an ion. You would take 200 milliseconds if you want to go from one end to the other. And so the average transport to get arbitrary connectivity would be something like half of that. You can go 2D, that's already a lot better. This was proposed quite a while ago, how you could do this. And in this case, we can assume an average area per ion of 100 microns squared. And that means that the whole system for 10 to the 7 would be 30 centimeters, so about a foot on the side. And then the longest distance would be on the order of 400 millimeters, just the diagonal here. And the transport time, it goes down to about 4 milliseconds at 100 meters per second if you want to go from one corner to the other. Of course, you can also think about going 3-dimensional. And in that case, it looks even better, of course. Now you have about a 44 millimeters per side cube. And the distance, the longest is 74 millimeters. And it takes about 740 microseconds. So it's still not great, but this is the worst case scenario. And of course, you need vertical transport somehow. I'll show you in a few moments how this could potentially be done. Anyway, so let's assume we go 3D. How would it look like? There's a whole half space that typically in ion trap experiments now is taken up by the imaging system. You need free view onto your ions, so you can't put anything on top of the surface trap. But if you don't need to do that because you have the detectors integrated, you get this half space to put more infrastructure in it. So one way it could look like is that the floors have all the electrodes to manipulate the ions and move them around. So the trap basically, and half of the gratings for the lasers. And then the ceiling layer could have the microwave electrodes that manipulate the qubit states of the ions and the detectors. You can do other layouts. This is just one example. And so the basic idea would be your qubits are somewhere here. The qubits and the helpers would be operated on by microwaves that can be applied to these antennas here. And in this way, you do all your qubit operations. And then when you want to read out, you would go to where a detector is in the ceiling here. And of course, you would only read out the helpers, as I hopefully explained to you. So the helpers would go into such a place. And then here's the laser beam. We are also good stewards. We want to recycle these laser beams, so we don't need quite as much laser power and don't have all these photons just fly out of the chip and be gone. So we would probably have another grating here that recollects the light. And then you can possibly reuse it. At least you know a little bit better where it's going, rather than just shooting it into the distance. Anyway, that's roughly how you could do this. And then finally, even more crazy, how can you change layers? How can you go between these different parts of the cake? One idea is that you could have a tapered RF electrode on the bottom and another taper on the top. And what effectively happens if you have that is that you hand the ion over from the bottom RF electrode to the top electrode. And then in this animation, at least, it can go up and go to the next level. So, of course, disclaimer here, this is pure science fiction. No one has built such a thing, but I think it's possible in principle, and maybe it will look different, but it's not crazy to think that you could go 3Ds with ion traps. Okay, this is my last slide, more reality. We will hopefully very soon prove the principles of these ideas all together in a single chip. So the plan is to have very gradient electrodes that can do RF and microwaves. And then we want gratings in this chip, so we can have laser beams. And we want readout for the helpers by having an integrated superconducting photon detector. And this is a collaboration that just started with Lincoln Labs. And so we'll see how much holds water of what I told you, hopefully. Finally, yeah, can we get this to work? Stay tuned. These are the people that did all the work at NIST, at least. This is our group, and I'm done, and thank you for your attention.